Hello, listeners. This is Mike, your host. If you are enjoying these archive episodes, please consider supporting the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange donate button or the Patreon link. Hopefully, with your support, I can continue to release these archive episodes. Thanks.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
Godspeed, John Glenn.
Roger, 0G, and I feel fine.
Okay, I'm on.
How does it feel for the United States to be the new record holder?
At last, huh? When that baby lights, there's no doubt about it.
Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
Listen, Tranquility Base here. The Eagle has landed.
That's one small step for man, one giant leap for mankind.
Hello and welcome. This is Michael Annis, and you're listening to episode 145 of the Space Rocket History Podcast. And now, Surveyors 2 through 7.
Development of the Surveyor spacecraft began in 1961. Detailed design specifications were issued, and hardware was built and tested. In May 1963, a mock-up of Surveyor was, for the first time, mated with Centaur hardware. At the same time, the first functioning prototype of Surveyor was being assembled. Many test design difficulties had to be overcome before Surveyor's complex terminal descent through the lunar vacuum could be simulated on Earth. The descent test problems were solved, however, and the terminal descent system was repeatedly verified before the first mission. In July 1964, the Surveyor prototype went through a mission sequence test for the first time. The prototype was later subjected to many severe environmental performance tests, including several simulated transits to the moon under solar thermal vacuum conditions. While the prototype was being tested, SC-1, the first flight spacecraft, was assembled and began its own series of tests. In March 1966, SC-1 was shipped to Cape Kennedy from the Hughes Aircraft Company. After extensive pre-launch tests and preparations, SC-1 was transported to the launch pad. On May 30, 1966, Surveyor was launched on its historic journey to the moon. On June 2, 1966, Surveyor 1 soft-landed on the moon. It returned over 11,000 photos and a large volume of telemeter data.
This episode will cover the remaining Surveyor Moon Lander series. The first lander, Surveyor 1, was covered in episode 75, so today I will cover Surveyors 2 through 7. The primary objectives of the Surveyor program were to support the Apollo landings by 1. Developing and validating the technology for landing softly on the moon, 2. Providing data on the compatibility of the Apollo design with conditions encountered on the lunar surface, and 3. Adding to the scientific knowledge of the moon. The Surveyor moon landers were designed and built by a division of Hughes Aircraft Company. Hughes Aircraft Company was a major aerospace and defense contractor founded in 1932 by Howard Hughes in Glendale, California, as a division of Hughes Tool Company. In 1948, Hughes created a new division of the company called the Aerospace Group. The Aerospace Group was further divided into the Space and Communications Group and the Space Systems Division. These two divisions built the world's first geosynchronous communications satellite, CENTCOM, in 1963, and followed it closely with the first geosynchronous weather satellite, ATS-1, in 1966. Later that year, Hughes designed and built the Surveyor series, beginning with Surveyor number 1, which made the first soft landing on the moon. The Surveyor program was managed by the Jet Propulsion Laboratory, JPL, in Los Angeles County, California. Now I'm going to describe the physical aspects of the basic Surveyor spacecraft structure. It consisted of a tripod of thin-walled aluminum tubing and interconnecting braces, providing mounting surfaces and attachments for the power communications, propulsion, flight control, and payload systems. A central mast extended about 1 meter above the apex of the tripod. 3 hinged landing legs were attached to the lower corners of the structure. The legs held shock absorbers, crushable honeycomb aluminum blocks, and the deployment and locking mechanism, and terminated in foot pads with crushable bottoms. The 3 foot pads extended out 4.3 meters from the center of the Surveyor. The spacecraft was about 3 meters tall. The legs folded to fit into a nose shroud for launch. A 0.855 square meter array of 792 solar cells was mounted on a positioner on top of the mast and generated up to 85 watts of power, which was stored in rechargeable silver-zinc batteries. Communications were achieved via a movable, large planar array high-gain antenna mounted near the top of the central mast to transmit television images. 2 omnidirectional conical antennas mounted on the ends of folding booms for uplink and downlink, 2 receivers, and 2 transmitters. Thermal control was achieved by a combination of white paint, high infrared emittance thermal finish, and polished aluminum underside. 2 thermally controlled compartments equipped with super insulating blankets, conductive heat pads, thermal switches, and small electric heaters were mounted on the spacecraft structure. The communications and power supply compartments were held at 5 to 50 degrees C. The command and signal processing compartment was held between -20 and 50 degrees C. The TV survey camera was mounted near the top of the tripod, and strain gauges, temperature sensors, and other engineering instruments were incorporated throughout the spacecraft. One, the photometric targets, was mounted near the end of the landing leg, and another on a short boom extending from the bottom of the structure. Other payload packages, which differed from mission to mission, were mounted on various parts of the structure depending upon their function. A sun sensor, canopus tracker, and rate gyros on 3 axes provided attitude information. Propulsion and attitude control were provided by nitrogen attitude control jets during cruise phases. During the powered phases, including landing, 3 throttleable Vernier rocket engines were used, and during terminal descent, a solid propellant retro rocket was used. The retro rocket was a spherical steel case mounted in the bottom center of the spacecraft. Each thrust chamber of the Vernier engines could produce 130 newtons to 460 newtons of thrust, and one engine could swivel for roll control. The fuel was stored in spherical tanks mounted to the tripod structure. For the landing sequence, an attitude marking radar initiated the firing of the main retro rocket for primary braking. After the firing was complete, the retro rocket and radar were jettisoned, and the Doppler and altimeter radars were activated. These provided information to the autopilot, which controlled the Vernier propulsion system to touchdown. Okay, let's move on to the missions. Surveyor 2 was designed as a follow-on to the highly successful Surveyor 1 mission. It was launched on September 20th, 1966 aboard an Atlas LV-3C and a Centaur D rocket at Cape Canaveral Launch Complex 36A. The The target landing area was within the Canis Medii. However, during the mid-course maneuver, one vernier engine failed to ignite, resulting in an unbalanced thrust that caused the spacecraft to tumble. Attempts to salvage the mission failed, and it impacted the Moon on September 23, 1966, at 3:18 Universal Time in the vicinity of 5.5 degrees north by 12 degrees west. Here's the clip for Surveyor 2.
In September 1966, SC-2 was launched. Unfortunately, a malfunction occurred during mid-course. After repeated attempts to correct the problem, the retro rocket was fired, and all contact with the spacecraft was lost 2 seconds later.
Now let's move on to Surveyor 3. Surveyor 3 was the second spacecraft of the Surveyor series to achieve a lunar soft landing. The specific objectives for its mission were to 1. Perform a soft landing on the Moon within the Apollo zone and east of the Surveyor 1 landing site. 2. Obtain post-landing television pictures of the lunar surface. 3. Obtain information on lunar surface bearing strength, radar reflectivity, and thermal properties. And 4. Use the surface sampler to manipulate the lunar surface and observe the effects with the television camera. Surveyor 3 was similar in design to Surveyors 1 and 2, but had several changes in the payload. It carried a survey television camera, soil mechanics experiments, and devices to measure temperature and radar reflectivity as on the earlier missions. But the TV camera had an extended glare hood. A surface sampler consisting of a 12 centimeter long by 5 centimeter wide scoop mounted on a 1.5 meter pantograph arm replaced the approach television camera. 2 flat auxiliary mirrors were attached to the frame to provide the camera with a view of the ground beneath the engines and one of the footpads. Surveyor 3 had a mass of 1,026 kilograms at launch and 296 kilograms at landing. Surveyor 3 was launched at 7:05 Universal Time on April 17, 1967 by an Atlas Centaur from Cape Canaveral Launch Complex 36B. After separation from the Atlas, the Centaur burned for approximately 5 minutes, putting the spacecraft into a 167-kilometer circular Earth parking orbit. The Centaur was restarted 22 minutes 9 seconds later, injecting the spacecraft into a selenographic trajectory. A mid-course maneuver, 21.9 hours after liftoff, aimed the Surveyor toward the selected landing point. On April 20th at 1:06 Universal Time, at 76 kilometers altitude, traveling at 2,626 meters per second, the vernier and main retro rocket were ignited by a signal from the altitude marking radar, slowing the spacecraft to 137 meters per second at time of retro burnout and ejection. Descent continued under control of the vernier engines and the Doppler and altimeter radars. A few seconds before touchdown, the radars lost their lock, apparently due to high scintillating reflections from the landing site. The guidance system automatically switched to an inertially controlled mode which prevented vernier engine cutoff. Touchdown on the surface occurred 3 times because the vernier engines continued to fire during the first 2 touchdowns, causing the spacecraft to lift off the surface. The distance between the first and second touchdown sites was about 20 meters, and between the second and the third was 11 meters. Engines were shut off 34 seconds after initial touchdown by an engine cutoff command transmitted from the ground. Initial touchdown occurred at 4:17 Universal Time, and final touchdown at 4:53 Universal Time on October 20th, 1967. As if all the hopping around was not enough, the spacecraft slid about 30 centimeters following final touchdown. Surveyor 3 came to rest on a 14-degree slope inside a subdued 200-meter crater in southeast Ocean of Storms, roughly 370 kilometers south of the Copernicus crater. Here's a clip.
Because its radar altimeter and Doppler velocity sensor lost lock, Surveyor 3's vernier engines did not cut off, and the spacecraft made 3 soft landings before coming to rest about halfway down the side of a crater 650 feet in diameter and 50 feet deep.
Initial photos were received within an hour of landing, and the surface sampler was used 2 days later. Surveyor operated throughout the lunar day until after local sunset on March 3rd. The lunar sampler was operated for a total of 18 hours, 22 minutes, digging trenches as deep as 18 centimeters, and the television camera returned 6,326 pictures. A large volume of new data on the strength, texture, and structure of lunar material was transmitted by the spacecraft. Images of an eclipse of the sun by the Earth and related thermal measurements were recorded. The last data were returned on May 4th, 1967 at 004 Universal Time, and Surveyor 3 failed to come back to life following the 2-week lunar night. Excessive glare in some of the images has been attributed to dust or erosion effects on the mirror due to the extended operations of the engines during touchdown. All Surveyor 3 mission objectives were accomplished. Here's a newsreel.
At the Jet Propulsion Laboratory in Pasadena, workers watch a living milestone in America's space exploration. Surveyor 3 is about to touch down on the lunar surface, the best landing ever. On target, the first photo shows its own antenna. A model of the 3-legged moon robot demonstrates equipment used to probe lunar land. It's a surface sampler which scrapes, digs, and drills. Tests of the space shuttle proved its ability to dig 2 feet into the ground. It also cracked 1-inch thick concrete. Powered by 4 motors, it can probe an area 24 feet square. The real moonship sent back pictures of soil samples, proving the moon surface is firm enough to support great weights. Well done, Surveyor.
Now for the really cool part. As an historical postscript, on November 19, 1969, the Apollo 12 lunar module landed within about 180 meters of the Surveyor 3 spacecraft. Astronauts Pete Conrad and Alan Bean visited the spacecraft on their second moonwalk on November 20th, examining Surveyor 3 and its surroundings, taking photographs, and removing about 10 kilograms of parts from the spacecraft, including the TV camera. These items would be examined once they returned to Earth. The Surveyor 3 camera is now on display in the Smithsonian National Air and Space Museum in Washington, D.C. Now, here's a clip of Pete Conrad and Alan Bean's encounter with Surveyor 3.
Fantastic sight. Al, look at the bottom of that crater. Here's some good rock samples right here. Come on. We stop here and look at the chart a little bit more closely. Man, does that LEM look small back there.
Pete, now we show you're 1,200 feet from the LEM.
Okay. You know what I feel like, Al? You ever see those pictures of giraffes running in slow motion? That's exactly what I feel like. Got the decided feeling I'm going to sleep tonight. Yeah, we're just going to move to the area Now look, you can see which way it came in. See the way this gear pad's dug in over there? Dug up dirt, you're still sitting there. Okay, Houston, I'm jiggling it. The Surveyor is firmly planted here. That's no problem. Okay, Al, we're ready to start getting a TV camera. Okay. All right, you see that material disintegrate. Hey, that cuts easy. Okay, 2 more tubes on that TV camera, and that baby's ours. Done. There you go. In the bag. Yeah, I gotta zip it up. Good show. How about let me cut this scoop off? Sure. Didn't think you were going to leave without a scoop.
Now let's move on to Surveyor 4. Surveyor 4 was launched on July 14, 1967 aboard an Atlas LV-3C and a Centaur D rocket at Cape Canaveral, Complex 36A. After a flawless flight to the moon, radio signals from the spacecraft ceased during the terminal descent phase on July 17, 1967, approximately 2.5 minutes before touchdown. Contact with the spacecraft was never reestablished and the mission was unsuccessful. The original landing target was 0.4 degrees north by 1.33 degrees west. The impact site is unknown. It is possible the solid fuel retro rocket exploded near the end of its scheduled burn. Here's the clip for Surveyor 4.
SC-4 was launched in July 1967. Unfortunately, all contact was lost just before touchdown. Which of several possible failure modes occurred had not been determined.
Moving on to Surveyor number 5. Surveyor 5 was the third spacecraft in the Surveyor series to achieve a successful lunar soft landing and the first mission to obtain in situ compositional data on the moon. The specific objectives for this mission were to perform a soft landing on the moon in the Sea of Tranquility and obtain post-landing television pictures of the lunar surface. The secondary objectives were to conduct a veneer engine erosion experiment, determine the relative abundance of the chemical elements in the lunar soil by operation of the alpha scattering instrument, obtain touchdown dynamic data, and obtain thermal and radar reflectivity data. Surveyor 5 was launched on September 8, 1967 at 7:57 Universal Time from Launch Complex 36B at Cape Canaveral on an Atlas Centaur rocket. The Centaur placed the spacecraft into an Earth parking orbit and then restarted 6.7 minutes later and injected Surveyor 5 into a lunar transfer trajectory. A mid-course trajectory correction involving a 14.29-second firing of the veneer engines was performed at 1:45 Universal Time on September 9th. Immediately following the maneuver, the spacecraft began losing helium pressure. It was concluded that the helium pressure valve had not reseated tightly and the helium was leaking into the propellant tanks, causing an overpressure which opened the relief valves, discharging the helium. A new emergency landing plan was quickly adopted. Early veneer engine firings were made while there was still helium to slow the spacecraft, reduce its mass, and leave more free volume in the propellant tanks for the helium. The burn of the main retro rocket was delayed at an altitude of 1,300 meters and a velocity of 30 meters per second, rather than the planned 10,700 meters at 120 meters per second. The new descent profile worked flawlessly, and Surveyor 5 touched down on the lunar surface on September 11, 1967 at 46 minutes Universal Time at 1.461 degrees north by 23.195 degrees east on a 20-degree slope of a 9 by 12 meter rimless crater in the southwest Sea of Tranquility. Touchdown was 29 kilometers from the original target. All experiments were performed successfully. Surveyor 5 returned 18,006 television pictures during its first lunar day. The alpha scattering instrument was deployed and performed the first in situ analysis of an extraterrestrial body, returning 83 hours of data on lunar soil composition during the first lunar day. A veneer engine erosion experiment was conducted on September 13th, about 53 hours after landing, consisting of a firing of the veneer engines for 0.55 seconds while the spacecraft sat on the ground to examine the effects of the engines on the surface. The spacecraft shut down from September 24th to October 15th, 1967, over the first lunar night. An additional 1,048 pictures and 22 hours of alpha scattering data were received during the second lunar day. On October 18th, Surveyor 5 acquired thermal data during a total eclipse of the sun. Transmissions for the second lunar day were received until November 1st, 1967, when shutdown for the second lunar day occurred about 200 hours after sunset. Transmissions were resumed on the third and fourth lunar days, with the final transmission occurring at 4:30 Universal Time on December 17, 1967. Pictures were transmitted during the first, second, and fourth lunar days. A total of 19,118 pictures were transmitted. Alpha scattering results indicated soil composition resembling Earth basaltic rock of 53% to 63% oxygen, 15.5% to 21.5% silicon, 10 to 16% sulfur, iron, cobalt, and nickel, 4.5 to 8.5% aluminum, and small quantities of magnesium, carbon, and sodium. The quantity of material adhering to the magnet was consistent with a mixture of pulverized basalt and 10 to 12% magnetite, with no more than 1% metallic iron. The veneer engine experiment produced minor but observable erosion of the surface. All mission objectives were accomplished. Here's the clip for Surveyor 5.
Though Surveyor 5 did not carry a surface sampler, footpad number 2 dug its own trench as the spacecraft skidded down into a small crater. The lunar soil appeared almost identical to that seen at the previous landing sites. Surveyor 5 carried an alpha scattering instrument. Analysis of that instrument's findings indicated that the composition of the lunar surface material is close to that of common terrestrial basalt. The magnetic materials test results agreed with that analysis.
Next up, we have Surveyor 6. It was the fourth of the Surveyor series to successfully achieve a soft landing on the moon. The specific primary objectives for this mission were to perform a soft landing on the moon in the Sinus Medii region and obtain post-landing television pictures of the lunar surface. The secondary objectives were to determine the relative abundance of the chemical elements in the lunar soil by operation of the alpha scattering instrument, to obtain touchdown dynamics data, to obtain thermal and radar reflectivity data, and to conduct a veneer engine erosion experiment. Surveyor 6 was launched on November 7, 1967 at 7:39 Universal Time from Launch Complex 36B. The Atlas Centauri booster put the spacecraft into an initial Earth parking orbit from which it was injected into a lunar transfer trajectory at 8:03 Universal Time. A mid-course correction maneuver was performed at 2:20 Universal Time on November 8th, and Surveyor touched down on the lunar surface on November 10th, 1967 at 1:01 Universal Time in Sinus Medii, a flat, heavily cratered Mare region at 0.49 degrees north, 358.6 degrees east, the center of the moon's visible hemisphere. On November 17th at 10:32 Universal Time, the Vernier engines were fired for 2.5 seconds, causing Surveyor to lift off the lunar surface 3 to 4 meters and land about 2.4 meters west of its original position. This lunar hop represented the first intentional powered takeoff from the lunar surface and furnished new information on the effects of firing rocket engines on the moon. It also allowed viewing of the original landing site and provided a baseline for stereoscopic viewing and photogrammetric mapping of the surrounding terrain. The mission transmitted images until a few hours after sunset on November 24th, returning a total of 29,952 images. The alpha scattering equipment acquired 30 hours of data on the surface material. The spacecraft was placed into hibernation for the lunar night on November 26th. Contact with the spacecraft was resumed on December 14th for a short period, but no useful data was returned, and the last transmission was received at 1914 Universal Time on December 14th, 1967. The results of the experiments showed that the surface had a basaltic composition similar to that found at the Surveyor 5 landing site. Engineering and soil mechanics data indicated the bearing strength of the surface was more than adequate to support human landings. This spacecraft accomplished all planned objectives. Here's the clip for Surveyor 6.
Surveyor 6's scientific payload duplicated that of 5, and its analysis of the lunar material also duplicated that found by 5, 460 miles east. Surveyor 6 returned over 30,000 photos, more than all 3 previously successful flights together.
And lastly, we have Surveyor 7, which was the 5th and final spacecraft of the Surveyor series to achieve a lunar soft landing. The specific objectives for this mission were to 1. Perform a lunar soft landing in a highland area well removed from the Mare to provide a type of terrain photography and lunar sample significantly different from those of other Surveyor missions. Objective 2. Obtain post-landing TV pictures. 3. Determine the relative abundance of chemical elements. 4. Manipulate the lunar material. 5. Obtain touchdown dynamic data. And 6. Obtain thermal and radar reflectivity data. Surveyor 7 was the only Surveyor craft to land in the lunar highland region. Surveyor 7 was launched at 6:30 Universal Time on January 7, 1968, with an Atlas Centaur from Launch Complex 36A. Touchdown on the moon occurred at 1:05 Universal Time on January 10, 1968, at 40.86 degrees south by 348.53 degrees east on an ejecta blanket about 29 miles north of the rim of the Tycho crater in the lunar highlands. Science operations commenced shortly after landing. The TV camera returned 20,993 pictures on the first lunar day. The alpha scattering instrument failed to deploy fully, but the surface sampler was used to force it to the ground. The sampler was later used to set the alpha scattering instrument on a rock and then into a trench it had dug. Approximately 66 hours of alpha scattering data were obtained during the first lunar day on the 3 sites. Operations were continued after sunset and included pictures of the Earth, stars, and the solar corona. Operation was terminated at 14:12 Universal Time on January 26th, 80 hours after sunset. The second Lunar Day operations began at 19:01 Universal Time on February 12, 1968, and included an additional 45 pictures for a total of 21,038 and 34 hours of alpha scattering data from inside the trench. Operations were terminated on February 21st. The lunar surface sampler operated flawlessly for a total of 36 hours, 21 minutes, digging trenches and moving and manipulating 4 rocks. Results were generally consistent with earlier missions, except that the chemical analysis of the highland crust showed it to be poorer in iron group elements than the previous samples, all from the lunar maria. The magnetic experiments showed the presence of magnetic constituents in amounts comparable to those at the Surveyor 5 and 6 sites. The lander also successfully detected laser beams transmitted from Earth. The mission objectives were fully satisfied by this spacecraft. Here's the clip on Surveyor 7.
Since potential Apollo landing sites had been adequately surveyed, SC-7 was assigned a scientific mission in an area just north of the crater Tycho. The spacecraft landed safely in the rockiest area yet encountered by Surveyor and supplied a vast amount of new data. The story of Surveyor is measured in more than just 5 successful missions. Surveyor accomplished what it set out to do. For the Apollo mission, Surveyor demonstrated conclusively that the moon, made up at least in part of materials comparable to those on Earth, can support man and his machine. The Surveyor spacecraft probed the physical and chemical nature of the moon and transmitted thousands of photographs. To land a man on the moon remains a national goal. Surveyor has contributed immeasurably to achieving that goal.
Now here is the final clip from JPL and Dr. Pickering summing up the Surveyor program.
The moon, not nearly as mysterious as it used to be, has been photographed, landed on, dug into, and chemically sampled. Surveyor 7 was the last in a series of unmanned spacecraft to land there. Reflecting on Surveyor's contributions, Dr. William Pickering, Director, NASA's Jet Propulsion Laboratory.
Surveyor accomplished everything that we had hoped for from that mission. 5 out of the 7 Surveyors which were launched landed successfully on the surface of the moon and operated on the surface. With the Surveyor photographs, we were able to show that landing a manned spacecraft on the moon is quite a reasonable undertaking, and in fact that the man will be able to walk on the surface of the moon without danger of falling through or sinking into the dust at any great depth. We were able to measure the bearing strength of the surface. We were able to get the general appearance of the surface, to point out that in certain areas of the moon at least, there were not very many large rocks which have to be contended with, but there were, of course, numerous smaller and smaller craters. We also found the first chemical analysis of the surface of the moon by Professor Turkovich's experiment, and this showed that in the areas that we landed, the rocks, or the surface material rather, was very similar to a basalt here on the Earth. We were also able to dig in the surface and get an idea of the feel of the surface as we went down a little bit below the surface. For a matter of a few inches, the material is very much like a soft sand.
Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage spacerockethistory.com and clicking on the orange donate button or the Patreon link. Thanks.